We will now proceed to the last part of this chapter, which is thinking recursively. At this point, we must remember that when we are designing a recursive function, we don't have to trace the entire sequence of calls. Thus, we just have to know if the function returns a value. Then, we must check that there is no infinite recursion. Eventually, a stopping case will be reached. We also need to check that each stopping case returns the correct value. And for cases involving recursion, if all the recursive calls return the correct value, then the final value returned is the correct value. Looking back at the power function that we had a while ago, it should be noted that there is no infinite recursion that was encountered. Notice that the second argument is decreased at each call. Eventually, the second argument must reach 0, which is the stopping case, causing our recursive call to stop. And this is how it's gonna be. It will reach a certain point where n will become 0, thus it would only return 1. It should be noted that each stopping case returns the correct value. For instance, given that we have the following arguments, which would give us x raised to 0, which is 1, which does the following. All recursive calls return the correct value, so the final value returned is correct. For instance, if n is greater than 1, recursion will be used. Thus, given the following arguments for our function call, this must return x raised to n minus 1. Thus, the following function call will give us the following. Thus, if we are going to implement that, we have the following codes. We also have recursive void functions. If we will recall, our first examples were recursive functions which does not return a value. The same basic criteria apply to checking the correctness of a recursive void function. We need to check that there is no infinite recursion. We also need to check that each stopping case performs the correct action for that case. We also need to check that for each recursive case, if all recursive case performs their actions correctly, then the entire case performs correctly. Let's take a look at another example, the binary search. As we mentioned a while ago, binary search works by allowing us to look for a certain value from a large array, which is assumed to be in order. To make the task easier, we are going to divide our large array into two, and depending on the value that we are searching for, that will decide which half of the array we are going to traverse. And a binary search can be used to search a sorted array to determine if it contains a specified value. Of course, the array indexes will be 0 through the final index. And of course, the array is assumed to be sorted. If the item is in the list, we want to know where it is in the list. Now let's have the definition of our problem for our binary search program. The function will use two call by reference parameters to return the outcome of the search. One, we're going to call it found, which will be of type Boolean. If the value is found, this will be set to true. If the value is found, the parameter location will be set to the index of the value that we are looking for. A call by value parameter will be used to pass the value to find. And this parameter will be called key. These are the pre and post conditions for the function that we will make for our binary search program. For our precondition, it is assumed that the array elements will be labeled A0 through the final index, which is the size of our array, and they are assumed to be stored in an increasing order. For our post condition, if key is not found in an array, found will have a value of false, otherwise it will have true. This is how our algorithm will look like. First, it would look at the item in the middle. If it is in the number we are looking for, then we are done. It means that the number has been found. Otherwise, if it is greater than the number we are looking for, then we will look in the first half of the list. If it is less than the number we are looking for, then we will look in the second half of the list. This is the first attempt at our algorithm. Of course, we are going to initialize this variable to false since we haven't found the number that we are looking for. And for this variable, we will set the middle of our array. And of course, if key is equal to the value stored in our middle element, therefore, we have found the value we are looking for, and we will also assign the index number to the location. Otherwise, if the key that we are looking for is less than our middle element, then we will search from index 0 through the index before our middle. Otherwise, if the key we are looking for is greater than our middle element, then we will search starting from the element after our mid through our final element in our final index. Since searching each of the shorter lists is a smaller version of the task we are working on, our recursive approach is natural. Then, we must refine the recursive calls. Because we'll be searching subranges of the array, we need additional parameters to specify the subrange to search. Thus, we will add parameters first and last to indicate the first and last indices of the subrange that we are going to search, thus giving us this first refinement. Again, we have the variable found, which is set to false. Then we set the value for our middle element. Same condition, if our key is equal to our middle element, found will be assigned a true value. Then we will also assign the index number of our middle element. Then, if the key is less our middle element, then we will search from the first index, which is in this case 0 until the element before our mid element. Otherwise, if the key we are looking for is greater than our middle element, then we will start from the element after our middle through the last index, therefore giving us the following variable names first and last. Of course, we must ensure that our algorithm ends. If key is found in the array, there is no recursive call and the process terminates. But what if the key is not found in the array? At each recursive call, either the value of first is increased or the value of last is decreased. If first ever becomes larger than last, we know that there are no more indices to check and the key is not in the array, therefore, found is false. Therefore, given the following considerations, we now have the final pseudocode for our binary search program. And we have the following. A case which will handle when the key we are looking for is equal to the mid element, thus reaching our stopping case, or if the key is less than our middle element, therefore allowing us to search for the key in the first half of our array, or if it is greater than our middle element, then we are going to search on the upper half of our array. If we are going to visualize what's going on, this is how it would look like. As we can see here, we have this array, then we are going to locate its middle element. Then, depending on the value of the key that we are looking for, that would also dictate which half of the array we are going to search, either in this half or in the bottom half. Then finally, we can write the actual code for our binary search program. As you can see here, this would be the interface or the declaration of our functions, indicating our precondition and postcondition. Finally, implementing it into an actual code, this is how it would look like. Anyway, a sample program for binary search have already been provided to you. So for you to understand how it works, I highly recommend that you run this sample program by yourself. And of course, we also need to check how our recursion for this particular example works. We must take note that, of course, there should be no infinite recursion, otherwise our program won't work. On each recursive call, the value of first is increased or the value of last is decreased. Eventually, if nothing else stops the recursion, the stopping case of first greater than last will be called. Each stopping case performs the correct action. If first is greater than last, there are no elements between our first element and the last one. Therefore, the key is not in this segment and it is correct to set found to false. On the other hand, if the key we are looking for is equal to the middle element, therefore, the algorithm correctly sets found to true and the location of the value that has been found. Therefore, both stopping cases are correct. For each case that involves recursion, if all recursive calls perform actions correctly, since the array is sorted. If key is less than the middle element, key is in one of the elements in our first half or our lower half if it is in the array. No other elements must be searched and the recursive call is correct. On the other hand, if key is greater than the middle element, then the key is in one of the elements in the upper half of our array. No other elements must be searched and the recursive call is therefore correct. How about the efficiency of binary search? The binary search is actually extremely fast compared to an algorithm that checks each item in order. The binary search eliminates about half the elements between the first and last elements from consideration at each recursive call. By looking at it, the binary search algorithm actually reduces our array into half subsequently until the key that we are looking for has been found or not. For an array of 100 items, for instance, the binary search never compares more than 7 elements to the key. For an array of 100 items, a simple serial search will average 50 comparison and may do as many as 100. For binary search, that can be done much quicker. Of course, we can also make an iterative version of the binary search program that we made, which was originally recursive. The iterative version of the binary search may be run faster on some systems. For instance, the algorithm for our iterative version is shown in this code sample. And as you can see here, it works exactly the same from that of the recursive version, only that this time we are no longer using recursive calls. Instead, we are only using a loop in order for us to repetitively search for the key that we are looking for. We have here another example which shows how we can create a recursive member function. I will leave this one for you to study, for you to see how this program works. As you can see here, this is already a familiar program that has already been given in the previous chapters in our lessons. But this time, this will be utilized for another version which will now give us a recursive version of one of its member function. Anyway, I will leave that for you to study and hope that you'll be able to experiment with its code for you to see how it behaves under different circumstances. So that would be all for this chapter, and I hope that you'll be able to explore our last example that we have here, which is the bank account example. This is the code which I've already provided to you. So please take a look at it and have an experimentation by yourself. So I guess that would be it. Thank you and have a nice day.